Welcome to this Forge College Explainer. Go ahead and grab your magnifying glass and definitely put on your blockchain detective hats because today, well, we're trying to figure out exactly why that custom Solana template you just built is suddenly completely broken. We're diving deep into debugging custom templates and best practices. As a pretty crucial part of our Programming with Solana track, specifically the Advanced Template Customization module, this is exactly where theory meets reality. This is where we learn how to turn broken, panicking code into a rock-solid, decentralized application.
Okay, let's just get right into this incredibly frustrating, but let's be real, totally normal scenario. In our previous lesson, modifying program logic and adding features, you built an absolute masterpiece. You added safe insertion points, you updated account layouts, and you probably felt like a total Web3 wizard. But today, the crime has been committed. Your client interactions are feeling left and right, and your program is panicking. Why does this happen? Well, because templates evolve. And when you start modifying complex logic, those pesky bugs just love to creep in.
So here is our game plan for today's investigation. First, we'll look at the crime scene. Second, we'll open up the detective toolkit. Third, we'll go over the methodology. Fourth, we'll round up the usual suspects. And finally, we will be closing the case. Let's get right to it.
Starting off with Section 1, the crime scene. Let's survey the damage.
Just notice the stark contrast here. You always start with this perfectly stable template that just hums along beautifully. But then you do what developers do, right? You add some new handlers, or maybe you refactor your account layouts, and suddenly it transforms into this chaotic mess of mismatched deserializations and off-by-one errors. Basically, your on-chain program and your client SDK start speaking two completely different languages. One of the absolute biggest friction points in Solana development is the PDA, or Program-Derived Address. A PDA is essentially an account whose address is mathematically derived from a very specific collection of seeds in a program ID. So if your client sends the wrong seeds, even if they are just slightly off, your program is going to outright reject the interaction. It's literally like trying to open a high-security bank vault with a key that's missing just a single tiny groove. Access entirely denied.
Moving on to Section 2, the detective toolkit. To solve these blockchain mysteries, you really need the right gear.
Your primary tools are going to include spinning up a fresh local test validator, and make sure you use that -- reset flag. Getting a clean slate is absolutely essential so old leftover data doesn't pollute your current investigation. Then, of course, you'll be building your own chain Rust program with Cargo build-bpf. When things inevitably go off the rails, you'll want to fetch your transaction logs from the Solana CLI using Solana transaction status, and pair that with the rust_log equals debug flag to see exactly what the validator is thinking behind the scenes.
Now, the really crucial part of all this is knowing where to look within your code, and that is exactly where the MSG macro comes into play. By strategically injecting this macro right into your REST instruction handlers, you can literally dust for fingerprints. You can omit values and log branch decisions to see exactly where your logic takes a wrong turn. It's honestly like leaving a glowing trail of breadcrumbs through your entire codebase, letting you follow the exact path of execution right up until the moment it crashes.
All right, let's hit Section 3, the methodology, because every good investigator needs a strict procedure. We're going to strictly follow this 4-step engineering blueprint to make sure we aren't just blindly guessing in the dark. Step 1, reproduce the failure deterministically. Look, if you can't reliably break it on your own local machine, you really can't fix it. Step 2, isolate the issue by mapping those transaction logs directly back to your source code. Step 3, apply your fix incrementally. This means you make the minimal necessary patch, not some massive sweeping rewrite. And finally, Step 4, run your regression tests to validate that your fix actually worked without accidentally breaking something else. Which brings us to Section 4, profiling the usual suspects. Let's interrogate the common culprits. First up in our lineup is the discriminator. You can think of it as a very strict name tag, or maybe a highly unamused VIP bouncer. If you alter this identifier in your Rust code, but you completely forget to update the client side, well, your program just looks at the incoming request, gets totally confused about what instruction you're even trying to execute, and just slams the door right in your face. Next up, we have the dreaded Borscht deserialized failed. Oh man, this infamous error essentially means that the data structure sent by your client simply doesn't match the exact field order or the exact size of the account struct inside your Rust program. The bytes just do not line up. It's exactly like trying to cram a square peg into a round hole. The program has absolutely no idea how to read the data, so it just panics. This table right here is going to be your absolute best friend.
It serves as your ultimate cross-reference cheat sheet for matching those painful symptoms to their quickest fixes. For example, if Borscht fails, you definitely want to check your account size and field order. If an instruction panics with an assert, it's highly likely to be an authority check mismatch, so go verify those signer flags in your client. And if you get that classic account not owned by program error, yeah, you probably passed the wrong PDA seeds or the wrong program ID.
And finally, Section 5, closing the case, because a solved case is completely useless unless it's documented.
Your final deliverable here is the debug report. This should be a concise, time-stamped artifact that clearly lists the discovered issues, the exact commit hashes of your fixes, and undeniable proof that your tests are actually passing now. And look, this isn't just busy work, okay? It's a living document in your repository that's going to make future migrations and security audits incredibly straightforward.
Now, for your template to be considered officially stable, your report has to check off all of these really strict validation criteria. You need to confirm your reproduction and isolation steps. You have to document at least 3 independent issues that you fixed. Your automated tests and both the program crate and the client absolutely must be passing. And lastly, your end-to-end client interaction has to be confirmed as successful, no exceptions.
Including these passing validation logs right in your report is essentially the ultimate mic drop. Actually seeing that beautiful OK for your unit tests and that glorious transaction succeeded message for your client interaction, it guarantees that your internal invariants and client contracts are explicit, thoroughly tested, and totally rock solid. So, the ultimate question you have to ask yourself now is your template truly stable and ready for cross-program invocations? Because now that you've mastered these debugging blueprints, you are perfectly positioned for our next module on cross-program interactions, where we'll actually wire this stable template into much larger flows. Huge thanks for joining this Forge College Explainer. Please do us a favor and visit forge.college to learn a lot more about this subject, access the tools we discussed today, and really dive deeper into a ton of other fascinating Web3 topics. Until next time, happy debugging.